Okay, so welcome everybody. So it's my great pleasure to introduce Georgios Dalezios. He's a postdoc researcher in the Aristotle University of Thessaloniki, and he will give two talks on stable and singular equivalence of finite dimensional algebras. And today is the first part of his lecture series. And please, Georgios, go ahead.
Okay, so thank you very much for the invitation to give these talks. It's my first time in this GANT seminar. So the idea is to give two talks. One will be completely introductory to certain basic concepts around this research area, because I know that not everybody here is necessarily familiar with homological methods in the theory of finite dimensional algebras. So the general idea of the talks will be to provide a historical perspective on the interaction between the following things. One, as I said, is the representation theory of finite dimensional algebras or of Artinian algebras more generally. And the path we will take will focus on categorical structures arising in this theory, such as triangulated categories, and also the use of homological methods. So more specifically in this first talk, that will be a bit basic, we will introduce certain classes of algebras as group rings or quiver algebras and say a few basic things about them. And then we will move to the Morita theory we have about module categories of these things or derived categories of these things. This is the plan for the first talk, and then the second talk will talk about more general classes of algebras like Gorenstein, introduce more general categories than derived categories, or like quotients of derived categories that are called singularity categories, and focus on equivalences of such categories. So let's start with a few basic things that everybody knows, like the prototypical example of a finite dimensional associative algebra in the representation theory is that of the group algebra of a finite group. So here K is a field, G is a finite group, and KG is the group algebra, which by definition is generated as a K vector space by the elements of G, finitely many elements in this case. And here the multiplication in this set is inherited by the multiplication we have in the group G. And this in fact makes it an actual ring, not just a K vector space. So it makes it a K algebra. And as I said, it's finite dimensional because the group we started with is finite. So of course we don't want to focus on groups themselves, but we need to study representations of groups. And I'm sure you know that a representation of the finite group G is given by a finite dimensional K vector space. I'm talking about finite dimensional representations together with a group homomorphism from our group to the automorphisms of this space. And if you remember the addition this space have, you can equivalently see a representation as a K algebra homomorphism from the group ring of your finite group to the ring of endomorphisms of this vector space. So in other words, representations are equivalently modules over this group ring. So it is a general thing that modules can be seen as ring homomorphisms from some ring R to the endomorphism of some abelian group. So in this way, you can imagine as a module as a representation of your ring. And the ultimate goal in representation theory of finite groups would be to classify all representations, or finite dimensional representations of your group at least, which is kind of hopeless. But the most classic and standard result here is from more than 100 years ago, is this theorem of Maske. Tells you that if the characteristic of your field does not divide the order of the group, so e.g. you can take just the the field of complex numbers for this not to be a problem at all, then any finite dimensional module can be decomposed into a direct sum of simpler modules, and these will be simple. So in other words, the group algebra is semi-simple, and should say that such decompositions are essentially unique by the Gorenstein theorem. Unique means here that any two such decompositions will have the same length, and after some permutations, the modules appearing there will be isomorphic. And this led later to Wedderburn structure theorem, which makes a general study of these semi-simple rings and produces some structure theorem around these, which you can use then in the special case of finite groups to get back a lot of information about your finite group G. So that was about group algebras. Now let's move to some other class of finite dimensional algebra, which is maybe less popular, but also well known. So here we start again with a field K, and now we take a graph which is directed that we call quiver. And I assume in this talk that my quivers have finitely many vertices and edges. And we define the quiver algebra. So to define this, you first define the concept of a path. So this is just a sequence of composable arrows in your directed graph. Composable means that the target of pi here should be equal to this and next. And we also consider some paths corresponding to the vertices of Q, and we call them the trivial paths. And here, in analogy with what you do with a finite group, you take the K vector space generated by these paths, and you imply some multiplication in this just by putting paths together, composable paths together. When this makes sense, you multiply them. When it does not make sense, so when they are not composable, you say that the multiplication of two paths is 0. So this creates a ring again, and because I started with a quiver with finitely many vertices and edges, this will be finite dimensional associative algebra again, this KQ. The unit will be the sum of trivial paths. So let's look at an elementary example here. Here I have taken the quiver Q with just two vertices and one arrow. So as a vector space, this will be generated by the two trivial paths corresponding to 1 and 2. And then the arrow alpha. I can see something in the chat. Don't we need acyclicity for yeah. We need acyclicity for this to be finite dimensional. That's correct, sorry. Yeah, we don't need loops or circuits in the quiver because this will create paths that do not stop, so the algebra will not be finite dimensional. Yeah, so I should have said that. So in this example here, we have this three-dimensional K vector space, and as an algebra, we can set up an isomorphism between these and something more classic, this ring of triangular matrices. So to set up this, you just biject the generators first. So you map the idempotents E1 to this matrix idempotent, and the analogous thing for E2. And then this nilpotent element is mapped to this matrix here. And if you check multiplication tables, here I compose paths as we compose functions from right to left. So if you see the multiplication tables for these two rings here, you can see that they are identical. So this gives us a K algebra isomorphism in this case. So this thing that looks a bit more tropical, this path algebra in many cases is something more standard. And we can also form quotients of such things. So we can take ideals inside this path algebra. And of course, the ideal has to be such that KQ mod I is finite dimensional algebra again, at least in this talk. These will be the ideals we will consider. So as an example here, again, you can take some loop. No, this is in relation to the comment in the chat as well. So we have to kill the loop at some point in order for the quotient to become a finite dimensional algebra. And you can easily set up an isomorphism of algebras between this quotient and this quotient of the polynomial ring here. As another example, I mean, again, here for this quiver, the construction gives you back something we know very well from other places. But in some cases, you cannot say anything like for instance, you can take this quiver and certain relations, either this I or J, and you can create the quotients, and these are finite dimensional K algebras. Probably you cannot express them as something well-known or whatever, but it's what it is. These are well-defined finite dimensional algebras. The representation theory of these is also very interesting, and it's also quite different depending on what kind of ideal you mod out with. So this here gives us an abundance of quiver algebras. So many finite dimensional algebras can arise, they have a representation by a quiver in this sense here. So if your finite dimensional algebra satisfies some mild assumptions, so here we need algebraically closed fields and some other technical assumptions, then you can always find the quiver Q and an ideal in the path algebra so that your algebra can be expressed as a quotient again. And if you want a hint about the construction here, you start with your abstract algebra and decompose it in a direct sum of left principal ideals like this. So these EIs will be idempotents that are primitive and orthogonal to each other, and the unit of the ring decomposes as the sum of these EIs. Then you can set up a quiver where the vertices corresponds to these idempotents, and then an arrow from J to EI is given, will be an element in this K vector space down here. The radical here is the Jacobson radical of your abstract algebra. For a quiver algebra, this radical somehow is generated by all the non-trivial paths. So if you mod out by radical square, you get the paths of length 1, which are the arrows. So this imitates this fact. So we have the rings now, the algebras, the quiver algebras, and I should tell you something about modules over these. So the module, there is the general definition of a module over such things, and some equivalent definitions of representations of your quiver in the category of vector spaces. I will not define all these things, but just a standard example, a representation or a module is just given by plugging vector spaces to the vertex of your quiver and k-linear maps corresponding to k-linear maps between these vector spaces. So of course, alpha and beta here should not be exactly as these, but no problem, you get the idea. So as another example, if you have this loop quiver here with this relation a to the n, then a module over this, you can think of just some v here together with some endomorphism, which is important. So of course, classifying representations over these things is connected to interesting problems in linear algebra, depending on the situation. But here we will take a more abstract approach somehow, and we will discuss about categories associated to these things. The most standard category that you can consider here is the category of finitely generated modules over your finite dimensional algebra. So here the objects are the modules, and the morphisms in the category are given by the homomorphisms of A modules. And what I will focus on in this talk will be on comparison between categories. So when can you say that some category associated to a finite dimensional algebra is almost the same as some other category associated to some other algebra? And of course, if you have an algebra isomorphism, this will imply that the two module categories involved will be essentially the same, but this is too much to have an algebra isomorphism. We just want the module theories of the rings to be the same, and by the same, we mean that we have an equivalence of categories, of module categories. In general, an equivalence of categories is given by functors going from one category, say A to B, and also some other functor G from B to A. And we want the compositions of these to be isomorphic to identities. There's some comment again here. Sorry, by module categories, you mean the categories of modules. Yes, exactly, yes. Yeah, either I say category of modules or module category, I mean the same. So the correct concept of equivalent is that of an equivalence of categories. And I just recall you here that a functor means, so it takes objects from one category to objects of the other category and morphisms of the other one category to the other. This cannot be completely random. Of course, it has to respect what you have inside the categories, which basically is the composition of morphisms. So if you have a composable pair like this, the images here need to be composable again, and you also want the identities to be respected. So what is a functor? So Morita has characterized this equivalence of module categories in this famous result here, which says that there is an equivalence of categories, of module categories like this, if and only if this equivalence can be realized by a tensor product, which is given by a bimodule. So it's given by a module, which is a module also on the left here for B and on the right for A. So this makes sense because you will input here some left A module and the output will be a left B module because M was chosen to be a left B module. So Morita has given a characterization of such equivalences. And this is part of a theorem of Morita. Actually, Morita also gave a few more conditions that are equivalent to these two. And it's kind of interesting that if the rings are Noetherian, you can also restrict to finitely generated modules here in this equivalence. So you might wonder how this module appears here from the abstract equivalence to this concrete equivalence down here. So because you have a functor, you have a map between these home sets from your module here, A to the A and the image of that. And this is an isomorphism because we say we have an equivalence of categories. So in particular, this will be an isomorphism. But in fact, this will be a ring isomorphism with compositions. And then this home A, comma A for your algebra is actually isomorphic to the opposite ring here. So this will create a ring homomorphism from A opposite to this endomorphisms of f of A. So this f of A has the structure of a right A module. And then you continue to show that these functors here define an equivalence. So these equivalences are quite nice because they preserve many invariants of the rings involved. So for instance, the center will be preserved. The center of a ring is the elements that commute with any other element by multiplication. So for commutative rings, this tells us that the Morita equivalence is just an isomorphism at the level of rings, because the center of a commutative ring is the ring itself, of course. Now, other properties are also invariant, like the semi-simplicity of a ring, or being left to right Artinian or Noetherian, and many other properties that you can express in categorical terms and are not very internal to the ring. This will be preserved because you have an equivalence of categories. Now, the problem with Morita theory is that it's a bit too strict. So if we look at this example here, again, here we have some matrix algebras, and I express them better here as some path algebras for two quivers. Here, the two quivers, you start with this 1, 2, 3, and then you have flipped the second arrow from 2 to 3, and you created this reflection here that goes from 3 to 2. So the module categories of these two rings are very close, but you can prove that these rings are not Morita equivalent. So by the module theories being close, I mean, here I have in mind the famous result of Gabriel that tells you that there is a bijection of indecomposable representations here for these two rings, because the same underlying, they share the same underlying diagram if you forget the orientation. And so they have almost the same module theory, but you can prove that they are not Morita equivalent. And this is an accepted deviation by now, so people have studied these more general equivalences. And in fact, here I've quoted that Bernstein, Gelfand, and Ponomarev, and also Auslander, Platzek, and Reiten made a systematic study of these functors called reflection functors now. So in this above example, for instance, here on the left-hand side, you have, say, the module category of A1, so the representations of this Q. And here on the right-hand side, you have the other quiver that you obtained by turning around the last arrow. And you can set up some functors describing this reflection at the level of categories now, at the level of module categories. And in fact, these functors can be also described as given by a tensor product or a home functor for some specific bimodule that you can construct. And this will be a nice relation between the two module categories. It will form an adjunction, but it will not be an equivalence of categories. But still, many nice properties will be preserved. So this leads, by work of Brenner, Butler, and Happel and Riegel, this leads to the concept of a tilting module. So just for general education, here's the definition of a tilting module, but we don't need to bother too much about it. So here it says that the tilting modules have finite projected dimension, so smaller or equal to 1 in this case, and will have no self-extensions. And here your ring will appear in a sort of exact sequence of this form. And if you have a Morita equivalence, the bimodules involved there will trivially satisfy these conditions. So this is like a generalization of these bimodules that appear there. And we will understand a bit better how these modules generalize Morita equivalences if we pass to categories of complexes, where things will be nicer there to describe. Here, again, this is introductory talk, so I don't know if everybody is familiar with categories of complex or derived categories and so on. So I will also define these concepts here briefly. So we can enlarge somehow this module category to some larger category of complexes here. The objects are given by chains like this. Here I have A modules and homomorphism between them. infinitely many of them, and then I want every time I compose two arrows in this to be 0. So these are the objects here, and the morphisms are given by this. If you have two complex x and y, the morphisms are given by these vertical arrows here, the FIs, and this has to be a commutative diagram. So every two paths you take, they will have to be equal if they have the same source and target in this diagram. And of course, the module category can be embedded in this because its module can be seen as a chain complex where the module is concentrated in degree 0. So one way to produce a complex from a module is by a free resolution. So here I've taken a module just finitely generated, and a free resolution just starts by surjecting from a free module into your module by this map. And of course, the surjection has a kernel, but you can do the same at the kernel again. So you can iterate this process, and you can build up, you can glue up together all these sort of exact sequences appearing here, and you can make a long sequence which will be exact. So this complex will have no homology. And this is by construction, this is a free resolution or a projective resolution of your module. So this is a way to construct complexes from modules. And this process, these resolutions are not unique, but they are unique in another category, which is obtained from the category of complexes. Here, this has objects are the same. They are again chain complexes, but the maps between two objects in this new category, they are given as a quotient, the homomorphisms from x to y in the old category. And here the quotient is generated by an equivalence relation, which tells you that two maps are related if and only if there are some diagonal maps here for each I, such that the difference between Fi and J can be taken as a sum, as indicated here. This is called the homotopic category. It's some concept that arises from algebraic topology, actually. So for us, it is important because projective resolutions will be unique in this category, in the homotopic category. And in fact, what is important is that a projective resolution, if you draw it in this form, so if you put the last map from P0 to N, if you put it vertical like this gives you a morphism of complexes, and the homology of the complex up here and the homology with the complex down there will be the same, isomorphic. So this map of complexes is a quasi-isomorphism. So in general, a quasi-isomorphism is a morphism of complexes which gives you isomorphism in homology. So this tells you that up to homology, your module is isomorphic to this complex up here. And then the idea is to create some category where I will not think of modules, but I will just think of complexes that are up to homology, they are isomorphic to my module. So this leads to the concept of derived category. So formally, this is obtained by the homotopy category, where we invert the class of quasi-isomorphisms. And this comes together, this comes together with a functor from the homotopy category to this derived category. And we want this map to turn quasi-isomorphisms to isomorphisms. So for instance, the projective resolution we saw in the previous slide, which is just a map in KR, if we pass to this new construction, will be a isomorphism. And we want this construction to be universal in a certain sense. Universal means that if you have some other category for some reason that does this job, so turns these quasi-isomorphisms to isomorphisms, then this, by some factor f, then this will have to factor through the universal construction. So any other that does the same job somehow is described via the universal construction, and for a unique factor u here, such that this diagram is commutative. So this is the concept of the localization of categories. So this is the best possible localization somehow. Every other will factor through this. And this somehow this resembles the situation of having a commutative ring and constructing a multiplicative you have a ring, commutative ring, a multiplicative subset, and you construct the localization. There is again the same universal property that arises here. It's an analogy of this. I think it's a direct generalization of this if you describe the rings as certain categories. And so the derived categories that we will consider in this talk will be certain subcategories of this derived category of A that I gave you in the previous slides. So the subcategories we will consider, they consist of, let's focus on this subcategory DB here. So this will be the homologically bounded complexes. So a priori, these are infinite complexes, but up to homology, they are bounded. And when I write DBA in this talk, I mean the bounded derived category of a module category of a finite dimensional algebra. For instance, if in your algebra, for some reason, every module has a finite projective resolution, and then this bounded derived category, by this process of taking resolutions, will end up being equivalent to a homotopy category where degree-wise of the complexes will consist of generated projectives in this case, because, as I said, everything is finitely generated here. And I should say a few words that these categories have different properties than the module categories you considered before. They are triangulated categories. So roughly speaking, this means that you have in your category, you have some automorphism, which means you have a factor sigma together with some inverse factor sigma minus 1. And when you compose these two, you get equal to the identity. You get that they are equal to the identity factor. So you want the sigma inside your category, and then you have a collection of diagrams like of this form, which are called triangles, and these satisfy certain axioms that I will not talk about now. And one of the axiom is that its morphism can be completed to a triangle of this form. So its morphism, you can find something like CF, some object, and a triangle like this. For instance, in this homotopy category, the automorphism will be the sixth factor. So for any complex, you just move it to the left, you define a new complex, sigma of x. At position I, this will have the module xi minus 1. And this C of f refers to the mapping cone construction, which I will not define. And by definition, the triangles in this homotopy category will be these diagrams where this is the mapping cone construction. And this will make Ka a triangulated category, and then the derived category, this would be A here. The derived category will also inherit the triangulated structure via this localization factor we talked about. So let's get back now to these algebras we had with the reflection here. We said that these were not Morita equivalent. However, the derived categories of these algebras are equivalent. And There is a beautiful result of Happel here that tells you that if you have two finite and acyclic quivers, then there is an equivalence of derived categories like this, if and only if the quiver Q prime can be obtained from Q after a finite sequence of reflections. So we can see how the concept of derived equivalence here nicely generalizes what was happening for Morita equivalences. In general, the definition of a derived equivalence between two rings, it's kind of obvious. Here I have finite dimensional algebras. I say that they are derived equivalent if there's an equivalence between the derived categories of the two. And there are many invariants that are preserved under a derived equivalence again. So of course, if you have a Morita equivalence, this will give you a derived equivalence. So all the invariants carry over, but if you only have a derived equivalence, there are many invariants that are still preserved. For instance, the number of non-isomorphic simple modules is preserved. The global dimension, if you know what it is, if it is finite for A, it will be finite for B if you have a derived equivalence between A and B. The growth-fitting groups are also preserved, and the algebraic K-theory of the groups, more generally, is also preserved. And some of these are formal consequences. Others are important results that need to be proved more seriously. But anyhow, you have many invariants still under a derived equivalence. And in this slide, I have included some result. I don't know very well about it, but I think it would be interesting for some people here. So there is here, if you consider the coherent sieves of the complex projective line, which is an abelian category, then there is a derived equivalence between the bounded derived category of this abelian category and the bounded derived category of the path algebra, which is given by this quiver, as indicated here. This is called the Kronecker quiver. So this is interesting, of course, because you have, so it's kind of different. Here you have an abelian category arising from somewhere else. No, I didn't start with the module theory or the module category of some ring here. But this is equivalent to the derived category of some path algebra here. And the equivalence can be constructed by taking the direct sum of the structure sieve of P1 and the structure sieve which is sifted by 1, and then you compute the endomorphisms of this, and this will give you this algebra here. So I don't know, for instance, a map from O to O1 given by multiplication by X and the other given by multiplication by Y. I think these correspond to these two arrows here in this quiver. You can set up a derived equivalence between these two, as indicated here. So it's not only for rings that we have these equivalences, they arise also in algebraic geometry and in other places. Now, about the general Morita theory of derived equivalences, there is a result of Ricard here, which generalizes tilting modules. So he defines tilting complexes, and a tilting complex will degree-wise consist of finitely generated projective modules over your ring A, finite dimensional algebra for us. And then you need some conditions. The first is that there should be no home from T to Ti whenever I is non-zero, home in the derived category, I mean. And the other is slightly technical. It tells you that all this category here, this KB proj, can be generated as a triangulated category by this add of T. So this is summand of finite direct sums of T, this subcategory. So in other words, the smallest triangulated category you can create out of this out of t with certain operations. This will coincide with the homotopy category of finally generated projectives. And then what generalizes Morita theorem is this famous result of Ricard here. Again, here, this is a part of Ricard's theorem because it gives more conditions in the original. So here, if you have finite dimensional algebras A and B, then they will be derived equivalent if and only if there is a tilting complex T and an algebra isomorphism from your ring B to the endomorphisms of this. And this is equivalent again to having an equivalence of triangulated categories between these homotopy categories of finally generated projectives. So this is more clear how it directly generalizes Morita equivalence, where the bimodule that appears in a Morita equivalence here is this T. So this is about the general theory. I can see that I have more time. So this is about the next talk, but the next talk will also start now. I have a tablet here. So this talk was about the departure of an equivalence between module categories of a Morita equivalence to an equivalence of certain triangulated categories, the derived categories. And there is also some other departure you can make by considering what is called stable module category. And these are related sometimes. And there is also some further category you can take here, which is called the singular category of a finite dimensional algebra. And you can also discuss about equivalences of such things as triangulated categories and study the relation between all the categories appear in this diagram. So we can start saying a few things about these. If I switch to tablet, I hope it will work. Okay, now I'll get confused. 1 second. You see this. So, can you see this? Can you see that I'm writing?
Yes,
Okay.
yes.
Right. So as I told you, there is. So we motivated this. We motivated the departure from these Morita equivalences to equivalences between derived categories, so derived equivalences. Now I want to talk about some further construction here and the equivalence related to this. So the construction will be that of a singularity category. Now for the definition of this, I will need to recall or define what is a perfect complex. So if you have a ring or Noetherian ring, say, then a complex of a modules will be called perfect if it is isomorphic in the derived category of the ring with a complex which consists of finitely generated and projective A modules, and it is bounded, strictly bounded. So now, why is this interesting for us, or for representation theory, or for commutative algebra? So there is a result here, quite classic, by Serre, Auslander, and Butzbaum. I'm not sure if I'm writing this correctly. Anyhow, this tells you that you have a local commutative Noetherian ring. And this tells you that the following are equivalent. So the first is that the ring is regular. So this means that the dimension of the ring equals the dimension of this maximal ideal, the unique maximal ideal of the local ring, modulo m squared, as a K vector space. So regularity is something in geometry, I'm sure some of you know. So this tells you that this condition is equivalent to every module having finite projective dimension in this ring R. And you can also do this for finitely generated modules. But what this tells you is that all modules in this ring are perfect. Because as we explained, they will be isomorphic in the derived category with the projective resolution. This is finite by this result. So this will tell you that everything is perfect in this ring. And this ring is regular, which geometrically is close to smooth, I think, at least over the complex numbers. If you have like a variety in some point and you consider the local ring corresponding to this will be regular if and only if you can define some kind of what's this called? Tangent space over the point. So this calls, how do I change the page here? So this category of perfect complexes, say for ring A, can be embedded to this bounded derived category of A. And you can form this, not exactly sort of exact sequence, but let's write it like this. I can see some comments here.
Yeah, Georgios, yes, can you go back to your previous page?
You need to be Noetherian from both sides. No,
yeah, yeah, you can answer.
No, actually, for the definition of perfect, I don't think I need Noetherian at all. I mean, Noetherian is for, you know, when I write in the next page, when I write a TBA mode, I want this to be an abelian category. So you can take left coherent or something for this. 2 or 3 are written are the same. No, they are not the same. This is, by this I mean all modules, and by this I mean finitely generated modules. This is capital M, this is small m.
It's difficult to see that.
Yeah, I'm sorry about this.
It looks similar.
Yeah, I'm sorry about this.
Difficult to see that it's small. Thank you.
Okay. Next page. So this category of perfect complexes is embedded in this bounded derived category, and you can take something called the Verdier quotient of these. Which is legit in this case because this has some nice properties, the Serre subcategory, so this always makes sense here, is well defined. So this is again a triangulated category, and somehow this thing here, at least when you have, say, a local commutative Noetherian ring, this corresponds, or we think of this as the smooth part of your ring. So taking the quotient of this is supposed to study the non-smooth part of your local ring. So this is why this quotient in general that I denote like this is called the singularity category. Now the question that I am interested in is, when do you have an equivalence of two related categories between, say, the singularity category of A and between the singularity category of B? And I will focus here in the case where A and B are finite dimensional algebras over a field K. Of course, whenever I have, there is another comment here. So why do we quotient the bounded derived category, not the unbounded derived category? You can also do that, but the theory is about homologically bounded complexes. I'm not sure if this is very convincing as an answer, but the definition is taken for homologically bounded complexes. So here, of course, whenever you have a derived equivalence, either bounded or unbounded here, these are equivalent. So say you have unbounded, then this restricts to an equivalence sorry, this should be B. This restricts to an equivalence of perfect complexes, which can be seen in a formal way also. These perfect complexes are compact objects, and these will be preserved rather than an equivalence. So as a consequence, you will have that the singularity categories are equivalent. So this somehow generalizes the concept of derived equivalence. And I should give you some example of a singularity category. So in the case of a group ring, for instance, say Kg is the group ring of a finite group G over a field K. And here there is another construction that departs from this module category and goes to some other category, which is called stable module category. And this is defined, is denoted like this. So it has the same objects as Kg mod. And here the morphisms in this category say whenever you have two modules, there will be a quotient.
Projectives.
There will be a quotient of what you had in the initial category Kg mod. This equivalence relation here tells you that if you have two parallel maps from X to Y, then they are related in this equivalence relation if their difference factors to a projective module. So I will motivate again this construction in the next talk. So let me move on because I want to finish with something. So how do you relate this with the singularity category? Here there is a map, like also a functor from Kg mod to the bounded derived category of Kg mod. And of course, you can continue here and take the quotient by perfect Kg module. So this will be the singular category of the group ring. And here, this factor takes projectives to perfect complexes, of course. So it will factor through the stable category. We'll give you a map like this. And this map is an equivalence of categories. In fact, I didn't tell you, maybe next time, that this is also a triangulated category here for a serious reason. So this is an equivalence of triangulated categories. I think this is a result of Ricard, also Bookweitz. We will talk about this next time. So in this case, I mean, this tells us that this singularity category, at least for a group ring, gets identified with something which is of interest in group representation theory. And in this special case, a singular equivalence is the same as asking for a stable equivalence between group rings. But I will not focus on group rings. I will focus on singular equivalences for larger classes of algebras, which will be the Gorenstein algebras, but this will be next time. So I will stop here for now.
Okay, thank you very much, Georgios.
Thanks.